Welcome to monochemistry, and today we're going to talk about a concept called intermolecular forces. Now you've probably already watched a video that explains the differences between inter and intramolecular forces, but let's just refresh our memories as to what it is. An intermolecular force is a force of attraction or a weak interaction or a weak bond, depending on how you look at it, between molecules. So in this case, in this particular picture here, this bond right here would be called an intermolecular force. See, we have one water molecule, two water molecules. It's the force of attraction between the water molecules. These bonds, these covalent bonds within the water molecules, would be considered intramolecular forces. Okay, so that's the difference. And what we're going to do today is we're going to learn a little bit about the different types of intermolecular forces and how they come about. And then we're going to look at how intermolecular forces help play a role in determining the properties of particular molecules. So let's start. Okay, so if the molecule is polar, so in order to tell what type of intermolecular force a particular molecule has, you have to use the skills we've been learning already, which means you have to be able to tell the shape of the molecule, you have to be able to tell whether or not the molecule is polar. And then from that, and from the chemical makeup of it, you can tell what type of interaction that it's going to have, okay? What type of intermolecular force it's going to have. So in this case, if the molecule is polar, there are two choices for intermolecular forces. The first one is called a dipole-dipole interaction. Now in this interaction, as you can see, we have two hydrogen chloride molecules, and they have an interaction between them that's called a dipole-dipole interaction. Now, how does that happen? As we know, in chemicals, bonds can become polar due to a difference in electronegativity. Now, sometimes those differences in electronegativity lead a molecule to become polar. And a polar molecule, of course, has two oppositely charged ends. In this case, there's a delta positive, or a slightly positive charge around the hydrogen, and a slightly negative charge around the chloride molecule because the chloride molecule has a greater electronegativity, meaning that it pulls the bonded electrons closer to it. And the same thing is happening on this side. And if those bonded electrons move closer to the chloride part of the molecule, then it will have a slightly negative charge because electrons have negative charges. Okay? Now, based on this slightly negative and this slightly positive charge, these two molecules are now going to be attracted to each other. And that is going to allow them to form a weak bond called a dipole-dipole interaction. Now, notice how we represent these intermolecular forces. We represent them as dashed lines because they're weak compared to the solid lines of a strong chemical bond like a covalent bond. Okay, so make note of that. Draw this picture and make sure you can explain, as I just have, how a dipole-dipole interaction forms. If you need to rewind the video and take notes, slow it down a little bit and take the notes, you should do that because you need to be able to explain why these two molecules are attracted to each other. Now I'm just going to move some things around here. And the reason I'm doing that is because there's a special type of dipole-dipole interaction, and that is called a hydrogen bond. So I'm going to bring out my hydrogen bond. You've already seen it. It was in the last one. A hydrogen bond is a special type of dipole-dipole interaction where you have, in particular, and I'll write this down for you, hydrogen bonding involves molecules that contain an O bonded to an H, or an N bonded to an H, or simply the HF molecule can also form hydrogen bonds. Okay? So here, any molecule that has an O bonded to an H, or an N bonded to an H, or this molecule here can form this special type of dipole-dipole interaction called the hydrogen bond. Now, hydrogen bonds are considered the strongest of the dipole-dipole interactions because, and here I'll show you why, because the electronegativity difference is so great between the oxygen and the hydrogen, or the nitrogen and the hydrogen, or the hydrogen and the fluorine, it creates a much stronger delta negative, and a much stronger delta positive. Therefore, this interaction is quite a bit stronger than this one here, which is just a regular dipole-dipole. Again, it's caused by the electronegativity difference. It's caused by the electronegativity difference. In this case, the oxygen is going to pull the shared electrons closer to it, forming a delta negative charge around the oxygen and a delta positive charge around the hydrogen. But again, in this case, because of the greater difference in electronegativity, the bond is actually stronger. This type of interaction is actually stronger. It's still weak compared to covalent, but it's stronger compared to the dipole-dipole interaction that we talked about previously. Okay, so in general, the more polar the molecule is, the stronger the interactions between it will be. Let's move on. So the other case, the other type of intermolecular force you're going to learn about occurs if the molecule is nonpolar. And those types of forces are called London dispersion forces. Now, I couldn't find a very good diagram of these. The other ones I just got from Wikipedia, and they were free, so I just took them and I used them. But for this one, it's a little bit more complicated to understand, and we're going to watch some animations a little bit later in the course that are hopefully going to explain this a little bit better. But for now, you're going to get a treat of me drawing a picture. Okay? So in general, you guys know that you have atoms, and the atoms themselves have a positively charged nucleus, and then around the atoms, in a three-dimensional, and it's going to be difficult for me to represent that, but in a three-dimensional area around it, you have what we would call an electron cloud. Okay, so in this picture, this is the nucleus with the positive charges, and this is the electron cloud. Okay, I'm just going to move this around a second here. Move those over here. London dispersion forces. Okay, so this is my first picture. I'm going to move that up here so it's a little bit more out of the way. Okay, now, we know that these have negative charges associated with them, right? Okay. Now, here's the thing. An electron cloud, the electrons are constantly moving. And because they're constantly moving, there may come a time when most of the electrons, or the majority of the electrons, end up on one side of the atom and not so much on the other. So as the electrons are moving around randomly, sometimes most of the electrons will end up on one side than the other. And that will cause a very, very small, slightly negative charge on one side of the atom and a very, very small, slightly, and these are like ridiculously small, even compared to the dipole-dipole, right? These are small. Okay, now if you get two molecules like that line up properly, then you can have a force of attraction between them. Okay, so this type of force, this London dispersion force, is based on the movement of the electrons around the nucleus. If the electrons end up all on one side of the atom, that will allow it to form a slightly negative charge, and the other side will have a slightly positive charge, and then two molecules will be able to interact in that way. And that's it. That's the London dispersion force. And again, we'll be learning a little bit more about it as we go through. Let's go on and talk about some of the properties that these intermolecular forces can play into. Okay, so there's lots of different things, and these are just a select few. These are the ones we're probably going to focus on in class, but these are the ones that we're gonna look at in this little video, and again we're going to reinforce that in class. So we have the boiling point, melting point, viscosity, surface tension, adhesion, and cohesion. Okay, so those are the things that intermolecular forces can affect. Let me give you an example. For instance, water. Water has the ability to form hydrogen bonds with itself. Therefore, the boiling point of water, because those hydrogen bonds need to be broken, the boiling point of water is much higher than molecules that do not have hydrogen bonding capabilities. Does that make sense to you? You have to break those bonds in order to boil the water. Why? Because the gas has to spread out, separate from one another. If those bonds are formed, those hydrogen bonds, then the water molecules can't separate from one another. Okay? Same kind of deal with melting point and these other ones. Here's what I want you to do, though. I want you to look up these and find definitions of all of these terms. That's the other part of the assignment. You don't have to explain how intermolecular forces affect them. You just need to look up the definitions and make sure they're in your notes. That in a nutshell is my introduction to intermolecular forces. Make sure you bring your questions to class, and don't worry, we are going to go over this a little bit more. There's some activities I have planned.